So what we were talking about last time is basically what we call rigid body kinematics, how sort of rigid bodies move. And let me sort of redraw the picture. We have a rigid body, and maybe we have 2 points, A and B, on this rigid body. And maybe the rigid body has some angular velocity, omega, in the k direction. And maybe it's got some angular acceleration, alpha, in the k direction as well. And we have two equations, one relating the velocities of A and B. So we have omega cross RA minus RB. And then the acceleration equation is this. So alpha cross RA minus RB plus omega cross RA with respect to B, okay? So this thing, RA minus B, is the same as RA with respect to B. I just happened to write it like this because I was running out of space there. Same thing, okay? So okay, it is convenient actually to write this equation, the second equation, in a slightly different form. So this equation, let's call this equation 1, equation 2. 2 is also equivalent to AA equals AB plus, so far exactly the same, RA with respect to B, let's say. And then this term, by the way, if you're going to do this cross product, these brackets, these parentheses are super important. You don't want to do omega cross omega first and then do RA with respect to B, because omega cross omega will be 0. If you take the cross product of a vector with itself, parallel vectors have 0 cross products. So really, these brackets mean something. So first you have to do this cross product, and then you do this with this whole thing is the correct thing to do. And the order in which you do the cross product does make a difference. It's not like regular multiplication. So first you do this, and then you do this. Super important. But you can sort of skip over all that by this sort of reduced formula. So it's basically, it turns out this is equal to omega square RA with respect to B, where this is the scalar omega. Okay, instead of using this vector omega cross R, you can do scalar omega square RA with respect to B and actually save on a couple of cross products. So you don't have to do cross products too much. Okay, so you can sort of, so it turns out this equals this. Okay, so easier to use. So this is easier to use, and then I'll probably use this version from now on. So let me actually just work out one random sort of made up problem, and then we will do sort of more, I guess, sophisticated problems, I suppose.
Professor, can you go back about the scalar omega? Can you repeat that again? What the scalar square, W square?
Oh, this is omega square. Omega is basically the angular velocity, right? So when we say omega, that's equal to omega cross k. This is the vector angular velocity. Right? And this is just the scalar component. Like if you have a number here, 3 radians per second, that's all that means.
Oh, so that'll just be omega square.
Exactly. Exactly. Okay. Exactly. All right. So if omega, the scalar, was given to be 3 radians per second, you just go 3 square equals 9 here, and then you just multiply that number 9 with whatever RA with respect to B is. Does that make sense?
Yeah.
Cool. Okay. And alternatively, you can take this vector and then do these cross products, and you will get exactly the same answer, if that makes sense. So just two ways of doing this. This is the way people would write sort of traditionally, but I think the book, as well as I guess we will use this as well. I mean, it doesn't matter which one you want to use. Yeah. In this case, you want to do a couple of cross products. In this case, you just take the square of whatever number omega is. Basically, you can either call it scalar omega, or you can sort of say, or magnitude of omega. Because you're squaring it, it doesn't matter if omega is positive or negative. You just take the magnitude and square it. That works too. Any other questions? Okay. So let me just do a problem that uses the acceleration formula. At end of last lecture, we used the velocity formula. But let's just use the acceleration formula example. So this is just sort of to get some practice. So let's say we have some point A, we have some point B, and let's say the point A is 2, 3, the point B is 4, 6, let's say, in Cartesian. So this is given. And let's say omega is given to be, I just said 3 radians per second, but so 3 radians per second anti-clockwise. And alpha equals, let's say, 4 radians per second square, let's say clockwise. Let me say it differently. This is omega vector. Okay, because I'm giving the direction as well. I'm going to call this a vector here. Okay. So you're given these things, and then let's say given a b equals, let's just say it's 3i plus j meters per second square. So all in meters, let's say. And what is AA, I guess is the question. Okay. So everything until here is given, and this is the question. And you basically just use this formula, except you have to interpret what we mean anti-clockwise and clockwise. So by convention, positive alpha is anti-clockwise, positive alpha and omega. Okay, so when we say 3 radians per second anti-clockwise, it's basically going to be omega equals 3k, of course, radians per second. And then when we say 4 radians per second clockwise, you would have to say alpha equals 4k with a negative sign, and then radians per second square. And this negative is because it's clockwise. Any questions about that? Okay, so when you say clockwise, you stick a negative sign. When you say anti-clockwise, you just use the positive thing. And then after that, what else do we have? Let's use, so this is a solution, I guess. Starts here. In all these formulas, we want to basically find RA minus RB. So basically we have R sub A is 2 plus 3i, 2i plus 3j. So we have, and then b is 4i plus 6j. And then we have, we wanted to find AA. So let's just write the formula out for AA. AA equals AB, which is given. Let me just rewrite what AB is. I guess it's right here. Okay, AB plus alpha cross R A with respect to B, and then minus omega square, where omega is now the scalar. In this case, it is 3, R A with respect to B. So before we plug things in, we can compute what RA with respect to B is. Let's do that here. So 2 minus 4 is minus 2. I, 3 minus 6 is minus 3j. Okay, so that's all we have. And then we just plug everything in. So we have this is equal to 3i plus j. So that's your AB. And then we have plus, we have alpha, which is a vector, which is minus 4k, crossed with RA with respect to B, which we just showed to be minus 2i minus 3j. And then we're going to do this omega square RA with respect to B. Omega square is 3 square. RA with respect to B is again minus 2i minus 3j. Okay. So that is it. That's going to be the acceleration of A once we sort of expand things out and so on. So just to get some practice, maybe we'll expand it out. So I'm just going to do that. And then all the negative signs are going to get canceled. So I'm just going to cancel them because negative times negative is positive. Any questions so far? And then we have, what do we have? I'm going to use not the determinant method. I'm just going to multiply it through. So I guess let me make these things. Anyway. Should I do that, or is that going to be misleading because I've converted the negatives to positive? In any case, let me just skip the negatives there. And basically 4 times 2, k times I, is what we have. And then we have 4 times 3, k times j. But it's a plus because negatives cancel. And then this is just 9. 9 2s are 18. The negatives go away, so you have plus 18i, 9 3s are 27j. I'm just going to power through this. 8 k cross I is, so if the cross products sort of go in the order ijk, then you get like k cross I is going to be j, because it's in the cyclic order. K I J K I J K, right? So it's in cyclic order. So this is going to be a plus j. K cross j, you're sort of going backwards. J is before k, so that's going to be a negative I. Okay, so that's the sort of way to remember it. And I guess that's it. So we can pull all the I terms together. 3 minus 12 plus 18. And then the j terms are 1 plus 8 plus 27. Hopefully we didn't do any arithmetic error, but oops. Okay, looks like there's a couple of questions on the chat window. Was RA and RB given? Yes, so Ryan asked, what was RA and RB given? Yes, RA and RB are given here. They're given as coordinates, and we just converted them into vectors here. So that's a question. And I was asking about what the cross products are, but yeah, so k cross I is j, k cross j is minus I, okay? I guess that's it. I guess I'll leave it at that. I won't simplify further. If you just want to recall the cross product principles I'm using here, the table is basically I cross j equals k, j cross k equals I, k cross I equals j. So basically this is going in the cyclic order, I, j, k. So if you're going in this order, it's a plus. And then if you're going in the opposite order, basically it's a minus. Okay. Any questions? Okay, let me do now come back to some sort of a conceptual thing briefly, and then we'll go back to doing some more problems. Well, imagine now the same rigid body, and let's say it's omega equal to 0, okay? Let's say it's omega equal to 0. What does it mean about its velocities? Like if you say, like if you have different points on this object, what is the relationship between the different velocities of the different points? They're all the same is the right answer. So what that means, so because, well, if you take this formula, the relationship between the velocities of 2 points on the object is 1 point velocity, other point velocity. Velocity of 1 point equals the velocity of the other point plus this term. With this term as omega, if the omega is equal to 0, then VA equals VB for any 2 points A and B, okay? So that's what this picture will look like. So if this point has this velocity, maybe I don't want to draw it in this, let me just draw it in the random direction. So if omega equal to 0, all points have same velocity. This is called pure translation. Okay, so this is called pure translation. And then you can imagine a situation where, well, let's say the whole object is rotating about a particular point. Let's say that you have a point O and say rotation about point O. Then what does that mean? Well, what does it mean about the velocity of point O?
0.
0, that's right. VO equal to 0. O is not moving. Okay. And then what does it say about the velocity of any other point? Let's take like this line, let's say. What does it say about this velocity? And we have some omega not equal to 0, right? What does it say about the velocity of this point that I just sort of marked here? Oops.
Is it perpendicular to the line?
Exactly. It's going to be perpendicular to that line because, well, it's rotating about, the whole thing is rotating about this point. So it's going to be perpendicular to that line. So it's going to be some velocity like that. What about a point here that's halfway between this point and this point? Same direction, half the magnitude is right, half the velocity is right. So basically, it's going to be in the same direction, but it's half sort of distance to it. So it's going to be half the velocity. If you take this point, which is maybe 3 times the distance or something, it's going to be bigger, and so on and so forth. So basically, the velocities along this line will obey, basically, will increase linearly with how far you are from the center O. Okay, does that make sense? And then if you take some other line, let's say, it's hard to now make up another line here, but let's say we take that line, then velocities are on this line are going to be again perpendicular to this point, and so on, right? Does this make sense? So that's going to be velocities of a point rotating about, of an object rotating about O. So velocities, velocity magnitude, scales linearly with distance from O and perpendicular to so if you take velocity Vp, okay, not perfectly written there, but just says velocity of P, the magnitude of that scales with scales linearly with distance from O, and the direction is perpendicular to any point. Okay, if you take this to be point P. Okay, and really that follows from this formula. It follows from this formula. Like you're imagining VO is basically 0, and VP is omega cross RP, basically. And omega cross RP is going to be perpendicular to RP and then scale with how big RP is. Okay. So this follows from basically saying VP equals V sub O plus omega cross RP with respect to O. This is 0. So this is just omega cross RP with respect to O. And yeah, so this is perpendicular Okay, cool. Sounds good. Okay. So that's if you have a pure rotation. Now imagine a third case potentially um, where you have some object and you're given the velocity of 2 points. And I'm going to say this is velocity of B. Okay. So the concept that we're going to talk about is called instantaneous center of rotation. Consider well, let me just say the high level principle, it turns out. If omega not equal to 0, then there is some point on or off the rigid body for which at some point, let's say q, I don't know, for which vq equal to 0. It's as if the whole rigid body rotates about q at the moment. And q is basically called the instantaneous center of rotation. Instantaneous. Okay, so how is this q determined? So what you do, let me just redraw this picture here. Let me, I guess, say omega not equal to 0. Let me redraw this picture. How to find the instantaneous center of rotation. So let me go to the next page. So some object here, and we have some point, and you know the velocity of this point, VA, and let's say we know the some other point here, and we know the velocity of VB, like so. To find this instantaneous center of rotation, draw given V of 2 points, draw perpendiculars to those velocities. VA, so let's say 2 points A and B, VA and VB, starting from, this is A, this is B, starting from A and B. And then where they intersect, intersection of these perpendiculars equals instantaneous center of rotation. Okay, so that's the algorithm. So let me quickly draw this thing. Let me maybe make a copy of it. So rather than draw on that picture, let me draw on this thing. So you basically draw perpendicular to this. So that's a perpendicular. You draw another perpendicular to this. That's a perpendicular. And that point is basically Q. Okay. So this point will have the property that, well, the whole object seems to rotate about that point. Well, you just draw a perpendicular. This velocity is clearly perpendicular to this line joining. This velocity is perpendicular to this line joining this point and this point. And really, that's kind of what we saw here. The whole object is rotating about that point. The velocities have the property that they're perpendicular to the line joining the center of rotation and wherever you are, right? So that's kind of what we have used to drawing perpendiculars to the velocity and seeing where the perpendiculars intersect. And if you just have 2 points, it turns out that's sufficient to localize the instantaneous center of rotation. Okay. Someone says, can you scroll up for a quick second? Let me scroll up. Lydia, where do you want me to scroll up to? Okay. And let me answer Ian's question. What if you have 2 or more than 2 velocities that you're concerned about? Would you have to find the intersection of those 3 lines? And Wyatt says they would all intersect at the same point, even if we had 3, right? Exactly. That's the answer. So however many points you have, the velocity is off. If you have 20 points, a million points, every point on this object, if you take 2 points and find the intersection point like this, you can do any other 2 points, they will all intersect at the same point, is the idea. Yeah. So perpendicular to VC for any C will also pass through Q. Okay, my handwriting is becoming worse, but okay. And Q can be off the body. That's right. So this is sort of where we started from. There is some point, a Q, which could be on the body or it could actually be off the body. So I guess that's that. So the instantaneous center of rotation can be outside the body. Okay. Okay. Daniel asks if there's, yes, this works even if there's, if it's a pure translation, it will not work. But as long as omega not equal to 0, this works. Okay, this is a very special case, 2 special cases, one of which is sort of Daniel's question. So 2 special cases where the above thing doesn't quite work or needs modification. If A and B have velocities that are parallel, okay? So if A and B have velocities that are parallel, like this and this, then they're perpendicular to those things. Well, what can happen there? Case 1, let me do it on the next page. So there are 2 cases there. Case 1 is when you have A, velocity of A is known, and velocity of B is exactly equal. Okay. So A, B, VA equals VB. Then if you know that velocity of 2 points on a rigid body are equal, what do we know about the rigid body?
The angular velocity is 0.
That's right. It's in pure translation. This implies omega equal to 0 or no pure translation. And then case 2 is velocities of A and B are not equal, but still parallel. And this can be true for any A and B. It is not like, when we say A and B, they are generic A and B. And if it's true for any two A and B, these things are true for anything, right? So let me just draw that rigid body. And let's say we have VA, and then we have some other point, VB is like that. It's parallel, but they're not equal. Now, what do we know about the velocities of these two objects? Or angular velocity of this object. Okay, that's right. So what you do, now there is rotation. Like pure translation, the only situation where there's pure translation is every point has the same velocity. If 2 points on a rigid body have different velocities, then it's rotating some manner. Then what you do is basically draw this line, extend it out, and basically connect the heads of these two vectors, and that's basically your Q. Okay, so this is the instantaneous center of rotation. So this is A, this is B, this is the instantaneous. Okay, and of course, it will necessarily be the case that this line, when you draw it, will be perpendicular to these things. That'll be the case. Does this make sense? Emily asks if VA and VB are equal in magnitude but opposite in direction. Does this work? Great question. Let's do that. And it works, yeah. So if you have A and then B, they can be equal or unequal. So let's just make it unequal potentially. But yeah, if they're in opposite directions, then what you do is you draw the line and basically you connect the heads of these arrows, and where they intersect is basically your Q. So this is VA, this is VB. This works whether these two arrows are equal size or unequal size. But yeah, cool. And then Ian asks, velocities don't have the same magnitudes for this more general situation in order to find the instantaneous center of rotation. That's right. Yeah. So in the more general situation, in this situation, yeah, these velocities need not be the same magnitude. They can be whatever magnitude. You just draw the perpendiculars. Where they intersect is the center of rotation. And then a special case where this will not quite work, because if VA and VB are parallel, then it won't quite work, because in this case, if you draw perpendiculars, basically the perpendiculars will be identical. So they intersect along a whole line, kind of, or they will be parallel. Anyway, so if VA equals VB, then pure translation. And then if they are unequal, then you can basically connect the A and B and connect the heads of VA and VB where they intersect. So basically the algorithm is connect and extend AB, connect and extend heads of like basically the tip of the arrow, VA and VB, and then intersection. And then the question that was asked, if they are in opposite directions, then the same algorithm works, connect AB, and then connect the heads, they intersect at some point. And a special case is when VA equals VB in magnitude, but that will still work. You will just have the point to be exactly in the middle. What is the first line you drew for case 2, Rohan asks. Case 2, this one is basically the line joining AB. So connect and extend AB, which will also happen to be the perpendicular to VA and VB. They will, they will be the same. It's both the perpendicular and the line joining AB, just because it's a rigid body. Yeah. Cool. Okay, so that's about instantaneous interpretation. We have about, I guess, 10 minutes-ish left. Let me begin a problem and see where we get. This won't be about instantaneous interpretation, but I guess it's just another example. And this is sort of the most common example that we will explore in the homework and exams and so on. And I'm going to introduce this system called the slider crank. Okay. So let me just draw these bar. That's like a rigid body. It's pivoted about this point. Okay, it's rotating about that point. And then we have, let me draw the other rigid body in a different color. Okay, and then let me something like that. I don't know, not a perfect figure here. Okay, so that's the picture here. So let's call this O, A, and then this point is B, like that slider, or this point is B. OAB is called, it's a mechanism. It's called a slider crank mechanism. Are people familiar with this mechanism? Have you heard of this mechanism before? So the idea is that, well, this thing rotates. And as this thing rotates, this thing goes back and forth. Okay? As this thing sort of rotates, this thing sort of goes in a circle and it gets pulled, and then as it comes back out, it gets pushed and so on. So as this thing rotates, this thing goes back and forth, or you can imagine this thing goes back and forth and this thing either rotates all the way around or sort of just rotates back and forth. Brian says I can visualize it. I've seen them pistons. Yeah, it says pistons, but that's right. Yeah. So how many of these do you guys think are in existence in the world? These kinds of slider crank mechanisms. It's probably, I don't know, I want to say a few billion or a few tens of billions, billions with a B, of these slider crank mechanisms, or a few hundreds of billions of these mechanisms out in the real world. Every internal combustion engine car has a few. This is like the piston that sort of goes back and forth, where there's like combustion happening on one side, combustion of fuel, which pushes this thing out. And eventually, I guess, that linear motion, combustion produces linear motion, which eventually allows you to drive a car or drive something rotational, I guess. This converts translational motion of the piston to rotational motion of this crank, I guess you call it. This is called the slider, this is called the crank. Linear motion of this, linear back and forth motion of this gets converted into rotational motion of this. This object is eventually connected to the wheel, and I guess that's how cars go. So roughly speaking. So this is called the slider. And this is the crank. And a few, I don't know, tens of billions in the world. All IC engine cars. Okay. I don't know if you have too much time to actually finish a problem, but let me start it. And then I'll just sort of set up the problem, and then I'll probably finish it next time. So the problems that you'll kind of see in this world is going to be, you will be given, let's say, the rotational motion of one part of a mechanism. It could be this mechanism, or it could be other mechanisms. But let's say you're given the rotational motion of this part, and then you'll be asked, okay, what's the linear velocity of the slider? Or what is the angular velocity of this thing? Or if you know the angular acceleration of this, what is the linear acceleration of this? Or vice versa, where you are given the linear velocity or acceleration of this, and you're asked to find the angular velocity or acceleration of this. So that's the kind of problem that you might see. So kinds of problems, let's say. Given omega of OA and or alpha OA, where OA is this crank. Find VB and or AB, linear acceleration, and or omega AB, where this is AB and this is a rigid body, and this might have some angular velocity. That's this thing, and or alpha AB. So that's the kind of problem that you might see. We will basically give you some of these things, and we'll ask about other of these things. I guess this kind of idea. QTY stands for quantities, I guess. Okay. Any questions? So rather than sort of try to solve this problem in the next 2 or 3 minutes, I think I'm going to mostly stop here But if you have any questions, I guess I shall answer them.